All right, let's get right into it. Today, we're going to be cracking open the hood of an operating system that really defined an entire era, Windows 2000. We're going way beyond the official manual to explore the hidden mechanics, the undocumented internals that systems programmers back in the day had to figure out all on their own. So here's our game plan. First, we'll set the scene. What was it like for developers back then? Then we'll look at the tools they used to peek behind the curtain. After that, we get to the good stuff, the actual secrets of the OS engine. And finally, we'll connect all of that to the world of software as we know it today. Okay, so try to imagine you're writing some really low-level code for Windows 2000. You've got the official documentation from Microsoft, right? But here's the thing. It didn't exactly tell you the whole story. And that, right there, was the core problem. The official device driver kit, the DDK, it looked really thorough on paper, but it deliberately held back a ton of information about internal features, hiding these absolutely crucial mechanics that developers needed to write truly advanced software. This created a huge gap in knowledge. And you know what filled it? These groundbreaking third-party books. See, while the official DDK was often super theoretical and honestly a pain to navigate, these cookbooks were all about practical hands-on learning. They gave you actual code samples and tools you could run to poke around the system yourself and see how it really worked. So, if you couldn't just read about it in a manual, how did you figure this stuff out? Well, you needed the right set of tools. Think of it like a digital forensics kit, but for a living, breathing operating system. The two main debuggers you had were the graphical WinDebug and this command line tool, i386KD. Now, what's really fascinating is that a lot of these serious, hardcore kernel developers actually preferred the command line tool. They felt it was way more powerful for that kind of deep system-level work. But the real game changer, the thing that made all of this possible, was the availability of symbol files, or PDBs. These files were the absolute key. They let the debugger translate all those raw, cryptic memory addresses into names we can actually read, like function and variable names. Suddenly, you weren't just staring at a wall of random numbers. You were looking at create file. It changed everything. And this is where it gets really, really good. Once you had those symbols loaded, the debugger gave you access to these special commands that were, for all intents and purposes, a secret decoder ring for the kernel's internal data structures. They were called bang commands because they started with an exclamation point. For instance, typing /process fields would just dump the exact memory layout of the undocumented eProcess structure. Since the official docs were totally silent on this, this was often the only way for a developer to figure out what data the kernel was storing for any given process. It was like a secret handshake to get the system to spill its own secrets. Okay, so armed with these amazing tools, developers could finally start mapping out this hidden territory inside the operating system. But what exactly did they find in there? What were the big secrets? Let's get into that core architecture. And we're going to start with one of the most fundamental pieces of any OS, memory management. Back in the Windows 2000 world, a really critical concept is the difference between how a program sees memory and how the hardware actually sees it. You had the virtual address, which is this private, clean, consistent view of memory that the OS gives to every single program. And then you have the physical address, which is the actual physical location on the RAM chips themselves. So the million-dollar question is, how does the system get from a program's virtual address to a real physical one? Well, it's this incredibly clever multi-level lookup process that uses the CPU's own hardware. The virtual address basically guides the system through a page directory and then a page table to ultimately find the physical page of RAM. You can think of it like a super efficient two-level address book for all of the computer's memory. Now, how does a regular program ask the kernel to do something important, like open a file? It does it through something called the native API, which lives in a library called ntdll.dll. This is the true, raw, low-level gateway to all the kernel services. It sits just beneath the more familiar Win32 API that most applications talk to. And this shows that journey perfectly. A call to the native API triggers a software interrupt, specifically into-EH. That's the knock on the kernel's front door. The kernel's handler then takes a service ID that the program passed along, uses it to look up the correct function in this master list called the System Service Table, or SST, and only then does it execute the request. Now, because this whole process was so structured and predictable, it opened the door for an incredibly powerful and, yeah, pretty dangerous technique called API hooking. If you had kernel-level privileges, you could actually go in and modify that system service table. You could redirect those calls to your own code to monitor them, change them, or even block them completely. Once you're inside the kernel, you start to see a pattern. You find that almost everything is managed as an object. Files, processes, threads, timers, you name it, they're all represented by these standardized data structures. And there's a central component called the object manager that handles their entire lifecycle, from creation to deletion. It provides this really elegant, consistent way to work with every single system resource. There's a special subset of these called dispatcher objects. And what makes them so special is a little header that makes them waitable. This is the core mechanism that allows functions like wait for a single object to work. It's how you can tell your program to pause and wait for a process to finish, or for a network packet to arrive. It's absolutely crucial for synchronization. And this object-based design was always being improved. One of the key evolutions in Windows 2000 involved this number, 3. The system moved to a more efficient 3-layered table system for managing all these object handles. It was a subtle, clever change from its predecessor, NT4, but it made a massive difference in scalability, allowing the OS to handle so much more activity. So, wow, we've really pulled back the curtain on the deep-down mechanics of an operating system that's over 2 decades old. But what does all this low-level knowledge really mean for us today? Let's do a quick recap of what we've uncovered. We saw the vital role that third-party tools played when the official documentation just wasn't enough. We traced the path a system call takes, from the native API through that interrupt to the system service table. We demystified that virtual to physical memory translation. And we saw that elegant object-based design at the very heart of the kernel. And that brings us to one last thought. We've just seen how intricate and complex the low-level layers of Windows 2000 were. Now, just stop and think about the operating system on your phone or on your laptop right now. How many more layers of abstraction do you think have been piled on top of those same fundamental concepts? Which leaves us with this final question to chew on. What does that ever-increasing abstraction really mean for software development? Does it make our lives easier, or does it just hide critical details we probably should understand? And maybe more importantly, in our totally connected world, what does it all mean for security? It's definitely something to think about.